In this presentation, I will be giving you an insight into the semiconductor growth of photonic devices, uh, which is meant for the summer internship 2021. And I am Sandeep Singh. I am a second year Ph.D. Working here at Tyndall on growth of 3-nitride devices, 3-nitride epitaxy. So I'll take you a step back. In the last presentation, Brian had already introduced you to the photonic industry, and it's which is kind of a mix of solar displays and cameras and different technologies, communication. So he already had summed you up on this particular thing and given insight into this particular thing. And in this presentation, I would like to take you to the core of the photonic industry, which is the photonics devices. And so what is a photonic device? A photonic device is defined as the most fundamental unit of a photonic circuit which can emit, absorb, or manipulate light traveling through it. It can be a LED, a photodetector, a modulator, or a power converter, or a solar cell, depending on your application. And to get more insight how we make this particular photonic device, I will take you through an analogy first. So you can see on the left-hand side, the construction of a house. From step 1, you make a foundation. Step 2, you go ahead and build the pillars. Then you make the wall. Then step 4, you go ahead with the roof, and then you complete your entire house. In a similar manner, Brian had already introduced you to vertical integration within the Irish Photonic Integration Center. And he had already talked about this in length in the last presentation. So I would use the same terminology, and we'll start with, we start with a substrate. We do epitaxy on top of that. We grow thin layers on top of that. That would be our first step, known as epitaxial growth. Then we fabricate our device, which is known as fabrication. And then we characterize this device and known as characterization. In this entire talk going ahead, henceforth, I will be talking about the process of the device and specifically the first step, which is epitaxial growth. My colleague, John, in the coming sessions will present you about the design aspect of this particular, how the photonic device is designed. And then Simon will walk you through the fabrication and hopefully the characterization aspect as well. So taking a step ahead, we first try to capture what is this entire thing is all about. What is this growth all about? It's a bit, what I'll say, kind of a tree, but we like to have a perspective in it. So what is growth? So growth is defined as a controlled phase transition which leads to a crystalline solid. Now, this can be from liquid to solid or gases / vapor to solid. And so we define it as dry or wet. So dry or wet process. Now, depending on this classification, they have other subgroups as well. So the dry process can be reclassified into thin films, how thick, and then the bulk process. Now, this is important because bulk process gives you the growth or conveys you the growth of the devices such as silicon bulk substrate, and sapphire as well. So, but the wet process can be reclassified into other process, which is known as sol gel and hydrothermal. For our interest, we would be clearly focusing on the dry aspect of the problem, dry aspect of the growth, and would be more getting into the thin film and the bulk of it. So the bulk is important because we have the CZ process, or we know say Zorlowski's process, by which we get the silicon substrate, which is utilized in our MOSFETs and those other devices. In the meantime, it is also used for photonic devices as well. I will also give you, okay, Krupowski process, which is a sapphire kind of thing. Now, thin film can be reclassified into epitaxial growth and deposition. Now, there is a very thin line of difference, and many times that line is very blurred when compared to differentiating epitaxial growth and deposition. But still, I would like to, the deposition can be attained using chemical vapor deposition. Okay. Now, this was evolved and utilized with epitaxial technology to achieve MOCVD. I will say MOCVD just because this technology is available at Tyndall and is used to grow devices, photonic devices, those epi layer devices which I had earlier shown you in the previous slide. So the similar approach is MB. You can grow the same layers with MB, but these are two different or concurrent parallel technologies which have their own pros and cons. So again, depositions are a lot of different types as well, so such as pulse laser deposition and ALD. So before getting into these all kind of depositions and epitaxial growth, I would like to convey you that this is a very small picture of actual growth. The real growth story or tree would be very huge, and I have tried to capture a very small part of it, which would be useful for specifically photonic devices. Those green arrows pointing shows what I am going to present in this particular, or what I am going to emphasize on in this particular presentation, and rest everything is like, okay, they are there, but we won't be talking about it. So to capture that, if you assume growth as a very universal set, okay, and I will say which is composed of lot of sciences and knowledge from maths, physics, material science, chemistry, electrical engineering, and electronics engineering. Now, all these sciences or streams work on different aspects of growth. So material, maths and physics may be working on the simulation and modeling part, whereas material science and chemistry would be looking into how these things is happening. Electrical and electronics engineering is just there to use the end product of the growth layer, and we will use it in our devices. So this is a very huge stream, and I'm just trying to capture a very small piece of it. Okay, sorry. So another subset of it would be epitaxy, where we are trying to grow thin layers on top of that. And the subset, if you consider epitaxy as a universal set, then MOCVD, which is also known as MOVP in many books, is a subset of it. You can find this entire thing that if MOCVD is a universal set, then 3-5 semiconductors. I will just, in the coming slides, I will come to you what is 3-5 semiconductor is a subset of it. And again, if you consider 3-5 as a universal set, then 3 arsenide, 3 phosphide, and 3 nitrate semiconductors is a subset of it. Again, there is 2-6 semiconductors as well. So in all this process, so what happens from the parent to the child? If you think like the tree concept, parent to child, there are some concepts which are derived and some unique to that particular system. Okay, so for example, if I say MOCVD has some unique characters and some physics which is derived from epitaxy. So that knowledge is superimposed with it and utilized ahead. In the similar manner, it goes, it passes on as you go deeper into the core of the technology. Similarly, I would say MB is also a parallel technology which can achieve the same kind of results, but the approach, or I would say the technology aspect, is a bit different. The growth and epitaxy is the same, but the process aspect, or I would say it's kind of a different. So, what is this? What are the merits of this particular epitaxy? They can help you achieve artificial materials, materials which were earlier not available, or I will say you won't find the ore of this particular material. You can make this material in your lab, and these materials have some unique properties, which I will come across in the next of the slide. You can control this in a very well controlled manner. The quality of these materials are very good quality. And the interesting part is you can create heterostructures of it. What is heterostructure? You can bring alloy of this particular, create alloys of this material, and you can interface the material one on top of the other, layer them, depending on their particular coefficient or critical, I will say, lattice constant, if they are lattice matching, kind of. The most interesting part, low contaminants. So because of this advantage, epitaxy is preferred means of growth for photonic devices. And so prior to taking you deep into the topic, I will first like to introduce you to the length scale which I'm talking about right now. So the length scale which we are referring, I will start with a 15 centimeter scale. Okay, I'll show you a €1 coin, which I think you all have seen. To convey you, the €1's diameter is 23.25 millimeter. So you can see how that places on a 15 centimeter scale. Now, if I zoom the 1 centimeter region, which is approximately equal to 10 mm, that entire region, once zoomed into, will be approximately 10 mm, and that is the thickness of a substrate. And this substrate which I am talking about, this substrate is the base layer which is used, base material, or I would say layer, base crystal which is used to grow devices on top of it. Now you can see the dimension of that particular would be 0.3 to 0.5 mm from a 15 centimeter scale, and in micron it is known as 300 to 500 micrometer. So you can see how thin substrate these are. Now this creates a actually problem in handling, actually, because they are very fragile in nature. Some of them are. So in the next aspect, we will have a look into a bulk growth. Okay, so growth of alum. Okay, it's a very common video which is available on the net, and I would like to, by this video, I'd like to give you an insight how growth is actually happening, because here in this video we can see it, and I think so. I will start the video and then I will give you an insight into it. So this bulk crystal is used, the seed crystal is so in this time lapse you can see that the seed crystal grows. In the meantime, there are other crystals growing at the bottom, which you can see, I think. And this is something like this is happening in our MOCVD reactors. So as you can see from this particular video, there is a seed crystal used to grow a bigger crystal. This was a kind of a solution phase. Okay, we are growing, this is in a different reactor. And so before taking you to the actual reactor, I will first introduce you to the materials which are possible here. So the semiconductor materials which are possible comes from this particular group or p block elements. You can see that this is the group 3 which I was referring to, and this is the group 5 which I was referring to. Now, if you mix these two group elements in a proper composition at a very high temperature, you can achieve materials which have unique properties. Unique properties like they can emit, absorb, or manipulate light. And on the right hand side, you are seeing the chart which conveys their energy band gap, or the region where they are most responsive, or that is the energy band gap, or where they respond to this particular interaction with light. On the x-axis, you are seeing the lattice constant of those materials. Now, this is important because these lattice constant will be used for calculation of mismatch, or whether you can put a material on top of another or not, and what will happen if that happens. So you see, these all materials are all belonging to the cation is belong to group 3, and the anion would be belonging to group 5 actually. And these are the semiconducting materials which we are available at Tyndall and are available at Tyndall, and different groups work on these materials. So now we will take in a lead and see what is epitaxy. If in the most simplest aspect I have to introduce you, I will say epitaxy is like arrangement on. I will again refer to you the same video which I earlier showed you and saw. So we require a base material and we grow on top of that. So it's more like following the same crystal. And in this figure, you can see that, okay, a substrate material, material or lattice is used to grow a film on top of that. Okay, you can see the lattice constant of the film and the substrate. Now, in the B figure, you can see that when you put it on top of that, there is a kind of a mismatch, strain kind of it. And this strain can be calculated from this particular formula, which I have introduced. Okay, lattice mismatch. And it's a very simple formula. So the lattice constant of the substrate, then the lattice constant of the film, and then you divide it with. This mismatch coefficient is very important because you can't grow any crystal beyond 15% mismatch, or it's very hard to grow that. Now, if the mismatch is a bit high, as you find in the strained film, the interface gets strained. That interface between these two materials, I will say seed crystal and the film which is grown on top of it. And that may lead to defects, half planes, or dislocations, which is detrimental for the device, the photonic device which we are talking about. And so this process is possible using MOCVD, or also known as MOVP. The full form of MOCVD would be metal organics, chemical vapor phase vapor deposition, or metal organics vapor phase epitaxy. These are the same synonym of each other. The thing is, they are used by a different group of people. In this schematic, you can see that, okay, the metal organics which are introduced are gases in form, and they come and react on the wafer surface. You can see different processes happening parallelly. And again, this substrate which is at very high temperature, so there are multiple processes happening, and whatever the left out are removed from the output. And so this kind of process happen, and this kind of process happen within this particular reactor on the right hand side. This is the metal organic chemical vapor deposition system available housed at Tyndall. So so whatever process which I showed in your previous slide, I would like to show you a simple simulation of it, and show you different growths which are happening within this particular, I'll say, within the epitaxy kind of. So there is one aspect which is island nucleation. In this kind of growth, there is kind of a nucleation which is forming over the entire surface, and rather than there would be a sheet or a layer forming, it should be it goes into kind of a 3D mode. So the atoms impinges on top of the layer which has grown rather than impinging on the substrate. So the white atoms which you are seeing are the foundation kind of, and the film or the substrate, and the red atoms are like the film which is growing on top of it. Now, this is an important growth from our epitaxy perspective, as the entire layer, this is known as actually layer by layer growth, or the entire layer will be finished or will grow, and then the other layer on top of that will start growing. And now you can see the second layer going on top of that. So I had already shown you the layer in these two slides. In this entire simulation, we saw the two different growth modes actually. So using the layer by layer growth, we try to understand what are the device which we actually grow. So we start with a substrate, which I also has conveyed as a bulk substrate. This can be silicon, gallium arsenide, sapphire, whatever it will be, depending on the device which you want to grow. Then I refer to you the thickness. This is important because it's 0.3 mm. I hope you understand how small and fragile it will be. Then we grow a layer on top of that, which is known as buffer layers. Then we grow the end contact of the device. Then we introduce this current spreading layer, which is on top of the end contact. Now, this is the most important region, which is known as active region. Now, this is either emitting, absorbing, or manipulating, whichever, depending on the device, actually. This is the peak current spreading region, and then the peak contact. This entire layer, if you think, this is only 2 microns, where rather this substrate is kind of a 300 micron substrate. So you can see that this would be very thick when compared to this. And just to show you this particular thing, these all layers have their unique character, which again, I'm not trying to capture within this particular presentation. Hopefully, in the coming presentation, John or Niall will discuss about this particular presentation, about this layer, and they again keep on varying depending on what device you are trying to grow. And you can see the dimensions which we are talking about. So to summarize this entire presentation, we discussed about, we had the semiconductor materials involved in the growth of the photonic devices. Process to achieve these semiconducting materials, which was MOBPE or MOCVD, and the layered nature of this process. So by this, I would like to sum up my entire presentation. Thank you very much.